Hi everyone and welcome. In today's lesson we are going to learn how to prove theorem 2. Now before we do that, let's just find out what theorem 2 means. Well, it says that the angle at the center of a circle is twice the size of the angle on the circumference of the circle when they are both subtended by the same arc or chord. Now there's three very important things in this theorem that you have to know is true before you can use the theorem. And the first one is that one of the angles has to be at the center of the circle. Now I'm indicating that angle here in purple for each one of our figures. There they are. And now we can simply go and show you why it is at the center. Because if you know that O is the center of the circle, then OB and OC are the two lines that makes this angle, and therefore OB and OC will also be radii. The same here, O is the center of the circle, so BO and OC forms this reflex angle. In other words, we've got the angle at the center. The same with this angle, because OB and OC touches the center here. They are both radii, so that's the angle at the center. So it's very important to know that this is the center of the circle. The second important thing is that the other angle should be on the circumference of the circle. Now let me show you. It's indicated here in all of our figures in blue. There we go. And now I can simply show you why it's on the circumference, because this line and this line that forms this angle touches the circumference there. The same with this angle and the same with this angle, because that line and that line that forms this angle on the circumference touches the circumference there. There we go. Now here's the third thing. Both these angles, the one at the center and the one on the circumference, has to be subtended by the same arc or chord. Now what does this subtended mean? Well, when we have a line and another line that forms an angle, it means that those two lines are connected at the bottom with this arc BC. This has to be the same arc, or if it was a straight line, chord that connects the two lines that forms the angle at the center. So the same here. This is a reflex angle, and its one side OB and its other side OC are connected by BC at the bottom. The same goes for this angle on the circumference, because AB and AC are connected by this chord BC. Now the same here, this angle here at the center with OB and OC, they are connected by this arc BC, and the same goes for this angle on the circumference. Both its lines or sides that form this angle is connected with the same arc. So it's very important to know, for this theorem to be true, both these angles, the one at the center and the one on the circumference, have to be subtended by the same arc or chord. Okay, now here's the proof. We are given circle O with angle BOC at the center of the circle. Now that's the purple one. And BAC on the circle. That's the blue one. And both angles are subtended by arc BC. Now we want to prove that angle BOC is equal to two angle BACs. So the one at the center, the purple one, is equal to two of the angles on the circumference. Now here we go. We're going to start with the construction, and we're going to draw line AOE. Now you can change this letter to anything that you want. It also depends on the letters in our figure that was given to us. But all that we want to do is we want to connect the angle on the circumference with the center, extend that line, and write our other letter. Same here. From the circumference through the center, extend it and write the other letter. From the circumference through the center, extend it and write the other letter. And now we can actually start our proof after we fill in these numbers. Now why do I fill in these numbers? It's simply to make the names of the angles a bit easier. Now when we start our proof, I'm going to start by referring to these red triangles that I show you here in the figure. And we are going to show that angle A1 is equal to angle B. That's the ones in yellow, as you can see here, here, and there we go. Now why are these angles the same? Well, because OB and OA for each one of our figures is the radii of this circle. So we can simply see that this red triangle in each of our figures is isosceles. So we can write angle A1 is equal to angle B because OA equals OB, both are radii. Now we are going to introduce our exterior angle, which is angle O1. Now there it is in yellow, I indicated 2, and that is equal to A1 plus angle B, because as you know, the exterior angle of a triangle is equal to the sum of its opposite interior angles. So we can write here this is true because it's the exterior angle of triangle AOB, which is the red triangle in all of our figures. Then we can simply go and say that angle O1 is equal to angle A1 plus angle A1. Now why 2 angle A1s? Because angle B is equal to angle 1 as we showed earlier. So we just substitute that B with angle A1. And now we can show that angle O1 is equal to 2 angle A1s. So we're halfway there because angle O1 is half of BOC and this half is equal to 2 of those. So now we do exactly the same for this blue triangle that I'm showing you here. Now, lucky for us, we don't have to write this entire part for the blue triangle too. We can just simply write similarly angle O2 is equal to 2 angle A2s. Now, this part of our theorem remains the same for all 3 our figures. Now, we are going to end this proof by only looking at these 2, and they have a different ending, and then later we will look at the ending for this figure. Okay, so here comes the difference between these 2 and this one. So here we go. Now we can simply say that O1, which is this part, plus O2 forms BOC. That's the angle we want. So when we take O1 plus O2, well, O1 is 2 A1s and O2 is 2 A2s. So if I add O1 with O2, I'm adding these 2. So I'm going to write that. 2 angle A1s plus 2 angle A2s. Then angle O1 plus angle O2 in both these figures form angle BOC. And here we do a bit of factorization. We take out the common factor 2 and then we get A1 plus A2. And as you can see, A1 plus A2 is BAC. That's the other angle we want. So now we simply substitute this part in brackets with angle BAC, and we've just proven our proof because angle BOC is equal to 2 BACs. Now we go over to this figure because it's a bit different. Now, this part stays the same. Let's just finish the proof off for this figure. Now, here you need to look very closely. If we want BOC, we are talking about this entire exterior angle for the blue triangle, and we've got this angle for the exterior angle for the red triangle. So to get BOC, we simply have to take this entire O2 minus O1. So instead of adding, we're going to subtract. So therefore, we're going to write angle O2 minus angle O1 is equal to, and if I take O2 minus O1, I take 2 A2s minus 2 A1s. So I write that down. Then we simply write angle O2 minus angle O1 is equal to the factorization of this part, which is 2 angle A2s minus angle A1. And then this part, as you can see, if we take this entire angle there minus this small part, well, we get angle BAC. So this part in brackets change to BAC, and angle O2 minus O1 forms BOC. And there is our proof done. Excellent. Now, what do we get from this entire proof? Well, if all of these things are true, then we can simply learn this abbreviation for application, which says that the angle at the center is equal to 2 times the angle on the circumference. So remember this abbreviation, it becomes important in application. See you again next time. Bye.